Should I use that?
I think it's an easy
Yeah.
Right. Well, good morning, everyone. To many people's surprise, I am chairing today's session. So it's my pleasure to introduce Robin, who I just formally met, and he will be discussing extreme internal waves. Please.
Thank you, Sam, for the kind of introduction, and thanks to the organizers for putting together this wonderful event. I've been enjoying the talk so far. Let me begin by saying that my talk today is a bit of an outlier in that it's going to be incompressible fluids, but I still think there's a strong overlap with many of the themes here. And in fact, in Kevin's talk yesterday, he has provided a nice point of a connection, right? The shallow water models which arise from incompressible oil, which are also effectively compressible, can describe phenomena like hydraulic shocks and roll waves. So here, instead of this discontinuity singularity in the solution, what I'm going to be discussing is another type of singular behavior in that it's really happening in the free interface, the geometry of the free interface. So more concretely, these two pictures, you will see them in later slides, but what I'm going to be considering is two incompressible fluid system, and two types of singularities to the solution. As you can see at the level of the interface, that one becomes like overturning or even what we say overhanging, namely developing vertical tangent or even past this vertical tangent, whereas the other making this contact point with a corner singularity. Okay. So let me also acknowledge that everything I'm going to be talking about is a joint work with Sam Walsh from Missouri and Miles Wheeler from Bath. Okay. So I know that it is, oops. To this audience, this slide might be redundant, but let me anyhow still go through everything, at least to fix some notations. So the problem I'll be considering here is 2D water waves, which is governed by the incompressible oil in the bulk, and here UMV are the velocity component affected by the gravity, and on top of the water region is vacuum, and the water surface is also part of the unknown of the system. So two types of boundary conditions are imposed. The one which is in black here is a so-called kinematic boundary condition, which basically says that particles on the surface will remain on the surface forever. And the other type of boundary condition, which is more exciting, which is where all these dynamic features are present, is the so-called dynamic boundary condition, which is essentially a force balance. So here we just use the pressure condition. Basically says pressure is constant, atmospheric pressure here. Okay, so this is 2D oil free boundary, a very challenging problem. It'd be too hard for me. So what we're going to be doing is to try to eliminate one independent variables, namely time. So we'll be looking at steady solutions, traveling waves. So put everything in this traveling frame, and we're able to eliminate time. So what you saw in the earlier slides, the t derivative now becomes minus cx derivative. Okay, so this is a steady water wave system that we are going to be looking at. So usually the first step that one can take to treat this free boundary problem is to try to fix the boundary. Okay, there are multiple ways to do it. So here we're just going to take advantage of the incompressibility. So we can introduce a so-called stream function, which is defined here. So basically, the velocity field is a 90-degree rotated gradient of the stream function, and somehow using this stream function formulation, we see that the interface, say, in particular, the interface becomes a streamline, a level curve of the stream function. And if you rewrite the whole system in terms of this psi, then you get this very nice Poisson's equation inside. This is a scalar equation rather than a system of equation. Okay, let me mention to you that omega here is vorticity. And the kinematic boundary condition just becomes this level curve condition. But there's a price you pay, which happens in the dynamic boundary condition, which was a constant pressure condition. Now it's written in this Bernoulli form, which is basically saying the kinetic energy plus the potential is a constant. Okay, so this becomes a fully nonlinear boundary condition. Okay. All right, so this is a basic setup for the 2D water wave. And if you remember from the title, I will be talking about extreme waves. So what does it mean? Okay, what are those waves? So here, the extreme wave, at least in the context of surface water wave, means that one has a stagnation point developed on the free boundary. What is a stagnation point? Stagnation point means that the point of the particle does not move in the moving frame. Okay, or you can say in the original lab frame, the particle moves together with the wave at the same speed. Okay, so in some other contexts, one can relax this condition from a full stagnation to a horizontal stagnation, which I will get into later. But somehow you see that if you look at this Bernoulli's condition, right? So having a stagnation means that the velocity is equal to 0, and the gradient square is the speed squared, right? So this term becomes 0, and then this y, which is a height, gets maximized. All right, so somehow the stream wave is also referred to as a wave of greatest height. Okay, so it turns out that from some elliptic theory consideration, when one reaches this kind of a extreme wave, this stagnation, the interface, well, the free surface can develop certain kind of a singularity, and this has been long observed back in the days of Stokes, 1880. He made this conjecture, this famous Stokes conjecture, basically saying that at this tip, where you see a full stagnation, the wave has to make a corner singularity, and he actually computed the corner, the size of the angle to be 120, okay, using some complex machinery, okay, because this is 2D, and okay, I have to mention that he's considering irrotational waves, so the complex machinery naturally comes into play. And what is remarkable is that it took about 100 years to rigorously justify this conjecture. And this is this big result by Amick Franco Toland, same time by Plotnikov. Okay, so that's the first rigorous proof of this Stokes conjecture. And it was later generalized in various contexts. And there's this also nice result by Wawruka and Weiss, which I will refer to later, which somehow gives a more sort of a geometric analysis flavor proof to this. Okay, so that's the extreme wave in the context of surface wave, and when there's no vorticity. Okay, and somehow in the numeric community, people found some more interesting extreme waves. So these are both numerics. Okay, this is by Talistas Silva and Paraguay in their 87 calculation. So both of these calculations are when you have some non-trivial vorticity, in particular constant vorticity. Okay, so these are a series of surface profile when you change the size of the vorticity. Okay, so you see that instead of developing this kind of a corner singularity, you see this surface become more and more round shape. Okay, they can even be like stacking on top of each other. Okay, which is kind of a crazy. These are exact Euler solution, right? They're not using any approximate model. Okay, and this kind of a solution is supposed to persist. Okay, somehow let me also point out that this kind of a overhanging, okay, cannot happen when there is no vorticity. So this can be, this has been proved by Spielvogel using some kind of a maximum principle argument. Okay, so you have to have some vorticity here. So here, but as soon as you turn on like a constant vorticity to the simplistic case, you can see this. Kevin.
You say it's expected to persist. Does that mean there's some experiment where they see this?
There are some pictures that Miles has shown me, like, not by him, but, where people see these beach waves, shallow, very shallow. As you can see, this, something like this, the depth is very, very small. And then you can see some kind of like a rounded bulb there. Yeah, those are some amazing pictures, but I didn't include them here. But these are all exact numerical computation, and there's even more exotic ones. This is done by Dyachenko and her in 2019, and you see that these are all periodic setting. I forgot to mention, and you see these bubbles. You can see as many bubbles as you want stacking on top of each other, okay, which is pretty remarkable. Yep.
How do they search through the configurations? I mean, how do they guess? What's the odds for guessing that?
Well, complex. You parameterize the curve, right, using complex variables, right, and then somehow you run everything in this complex machinery, and there is a nice, very numerically friendly way to formulate this problem, and then you can unravel the parameterization, and you see this. This has been very well developed in 2D, in the 2D context. And I say there is vorticity, but it's constant. So somehow, it's kind of nice that if you just mod off a linear shear, which corresponds to this constant vorticity, then the rest becomes irrotation. So there's still like a way to make the calculation work. So these are all numerics, right? So what happens? What about analysis, right? Is there any analytical justification, right? So toward that, there's this big paper by Konstantin Strauss and Wawruka in the 16, where they basically considered exactly the same setup as in those numerical results. Constant vorticity here, there they considered periodic setting, and they were able to use global bifurcation machinery to prove. Well, I should say to provide a framework that potentially allows a configuration like this. All right, so what's left over from there is that whether or not one can definitively get those overhanging waves is still a question. But in their formulation, basically say that at the end of the bifurcation, certain things can happen, among which this overhanging is one alternative, okay, which is already very, very hard, remarkably hard. Okay, and some follow-up results. This is one by Wellen and Weber 2 years ago, where they generalized this constant vorticity to a more general vorticity. And in Susanna Haziak's thesis, she considered variable density. But the results are more or less similar, by which I mean that they're using global bifurcation, and they prove that at the end of the bifurcation curve, overhanging or overturning is one of the alternatives. The other alternatives are like corner singularity, or touching, like you see in here. Okay, not necessarily overhanging, but like overturning. So I forgot to make this distinction. Overturning, by overturning, I mean just developing this vertical tangent. Overhanging is way past this, so the profile becomes multivariate.
These are both.
Yes, these are both. But this touching is somehow due to the fact of periodicity, because they are considering periodic waves, right? So here, these two are examples of the solitary setting, okay, where you have an infinite extent of the fluid, And this is the work by Hazel and Wheeler, where they considered exactly this constant vorticity, but it's in a solitary wave setting. And here we last year we had a result where the vorticity is very concentrated. It's a point vortex. Okay, and this is a numerical calculation. Okay, this is like a cartoon that they had in their paper, but this is a calculation. We, as you can see, there's a point vortex centered here, and you see this very much like a disc-shaped bulk of fluid hanging on top of this very shallow infinite extent of water. So all of these analytical results, as I said, yep.
Is there a link with the works of Lobo in interface in the case of the network stability and
That's a good question. That's a good question. Here, this is surface wave. All right, so you're talking about this Rayleigh Taylor type. Yeah, we didn't pursue in that direction because this is only, all of these are steady solutions, right? We're not yet able to look at the dynamical setting. But there is a common belief that they are unstable. But so far, nobody can prove it. Yeah. So I mentioned those analytical results which potentially allow the overhanging waves. So far, there's only one rigorous proof that I can find, which actually proves that these crazy looking waves exist, and that's just occurred early this year. Davila, Del Pino, Mussel, and Wheeler, the Bath team, they proved in a perturbative setting, which I will explain shortly, the existence of this overhanging, very like extremely overhanging, which I will explain again. But basically, the picture looks like this. So you have almost like a round disc bulb of fluid, right, connected to this almost flat, shallow extent of water through a very thin neck here. Okay, so it's a gluing technique. It's perturbative, and roughly speaking, somehow it has been well known that if there's no gravity, okay, if you just look at Euler, free boundary Euler, if there's no gravity, you can use complex machinery to build up exact solutions, bunch of exact solutions. One of which being like an exact disk of fluid touching with a horizontal strip of fluid. That's their starting point. All right, they start from there and they sort of turn the gravity on by a little bit. So they perturb the gravity a little bit. So they open up this neck and through some very delicate analysis, they manage to glue them together. Okay, so this is a perturbative result, but this is probably the only rigorous justification I can find, which proves the existence of these waves. Okay, this is a small gravity result. Okay, so that is for the surface wave. Okay, but my focus is on internal waves. So this is the picture. All right, so instead of vacuum versus fluid, I have two fluids. Okay, I have two fluids. So the problem becomes a little bit more complicated because now you have dynamics from both regions, okay, rather than just the one fluid region. Okay, so that's basically the picture. And in terms of the extreme waves, or in particular those overhanging waves, again, the numerics community has long been aware of this overhanging feature. Okay, so this is even earlier by Hoyer. Okay, in the late 70s, she was able to compute, even back then, the internal wave profile all the way up to this very much like a vertical tangent development. Okay, and later, Mayron and Safman, Turner Vanderbroek, and Pulling Grimshaw, they reconsidered the same setting. And you can see that the calculation basically shows that the wave will overturn and even overhang, for sure. Okay, let me just point out this kind of an upside down picture is due to for whatever reason, I still don't quite understand, Pauline Grimshaw decided to turn the gravity upside down. So that's why the picture is like also upside down. Okay. And some more recent calculation. This is in the 2020. Okay. There's even more exotic. So these sort of, they call this kind of a mushroom looking Stokes bubble are like, these are the exact numerical computation, and the conjecture they are making is that at the end of the bifurcation, what one can see is a whole stagnant fluid bubble. They call it Stokes bubble, sitting on top of a Stokes corner. Okay, so very exotic looking. Okay, so the analytic, from the analytic perspective, right? So same question can be asked. Okay, you know, we've seen this kind of a numerical evidence of the existence of those crazy waves, but can one actually prove that they actually exist? All right. So the tool that we are taking is from this global bifurcation, but there is like the one common sort of downside of this global bifurcation is that although it's very powerful in constructing waves away from the perturbative region, but if you want to decide what happens at the end of the bifurcation, you always have multiple possibilities. Okay, as I said, you could have the singularity coming from the corner formation or coming from this development of vertical tangent, or you could have some other quantities blowing up, right? So which one is actually happening is a big question. All right, so that's sort of what we decided to tackle. Okay, so that's for the background. So let me get to, well, I think I forgot one more. Before I get to the real mathematical setup, there is one other interesting feature of this internal wave setting, okay, which you can't see from this surface wave, so which is termed as gravity current. So what is a gravity current? This can be more or less explained from this lab snapshot. All right, so okay, let me just quickly explain to you what these things are. So consider this like in a wave tank, and you have two types of fluid with different densities. The darker one is heavier. This lighter one is lighter. So they're separated by a vertical gate. And at a certain point, you lift the gate open, and the denser one will intrude into the lighter region. If you waited for a little bit, and you can see a very kind of a steady wave pattern forming, which is exactly like this. Okay, which looks exactly like this. This can be very easily regenerated. I can even, well, it's, you know, if you search gravity current on YouTube, you can find tons of experimental movies. So this is one I would like to show you. So that's exactly like what I described, right? The green one is kind of like you know, the heavy one, right? And you see this kind of a pattern being very steady, right? Very steady. So yeah. And this kind of a phenomena can also happen in lots of other physical contexts. Okay, so among all of these I listed, I want to point out this haboobs, which is like dust storm, and I think I do have a movie, which is from last year in Arizona. This is a bit long, but let's take a look. And these I don't know if you can see these moving white dots are cars. That's how big this dust storm is. If you wait a little bit, you see that, right? Which is very much like what you saw in the wave tank, right? It's very remarkable, and there's more. There's more of those, okay? Those are quite remarkable. Okay, and this tip seems to be quite consistent, right? And that'll be a big part of the story. Okay, so this gravity current has been a very important subject in the applied community. There's tons of papers studying this gravity current, and here I want to point out a very influential one by von Karman, when I think this is from a 1939 lecture of his at Ohio State, where he proposed a very simple model to describe this gravity current phenomenon, which is exactly like these two fluid system. So in his proposal, right, there's a lighter fluid sitting on top of a heavier one, and this heavier one is completely stagnant. Okay, and there is a triple junction point here where that's the sharp angle is taking place. Okay. And somehow, you know, about 30 years later, Benjamin's kind of reevaluated von Karman's model. My rough reading, together with the discussion with my collaborators, it seems that Benjamin didn't like von Karman's proposal for whatever reason. But somehow in the end, he agreed with all of the conclusions. Yeah, I can't really tell. I can't really adjudicate the evaluation. But somehow Benjamin also proposed a relevant model, which he called a cavity front, which is sort of like an upside down situation of the gravity current. So instead of lighter on top of heavier, you can have a bubble, a cavity bubble on top of a fluid, and the fluid is emptying out in one direction and pushes the bubble to the right. Okay, and somehow, you know, at the place where you see this triple junction contact point, one could expect a certain kind of a singularity happening. Okay, so what would the angle be? 120, just like the Stokes, which is kind of like not a big surprise. At the back then of von Karman, there's no rigorous proof of Stokes yet, right? So what he basically did is to follow what Stokes did using this complex machinery, right? So he basically, one can assume the existence of such waves and run this kind of asymptotic expansion, and then you calculate it carefully enough the power, and you get this 120. Okay. And there are many other extensions later on, which I won't go too much into. But somehow, what's a bit frustrating to us is that not only hasn't this kind of a contact angle been proved, there's not even an existence of such wave, right? So all of the numerics or this formal calculation are based upon the assumption that these waves exist. Okay, but there is no rigorous proof. Okay, so this is another thing that we're kind of chasing after. All right, so now let's get to the equations. So once again, this is a picture that I want everybody to have in mind, right? So this is all steady internal waves. So everything is put in this moving frame, right? So we're assuming that in the upstream, everything is uniform, right? And of course, we're looking for a solution of front type. So the upstream state is distinct from the downstream state. So for sure, you cannot expect to have a uniform flow downstream just from mass conservation, right? So you will necessarily see some kind of a vortex sheet developing downstream. Okay, and I have two density flows in the two regions. So the subscript 1 means it's a lower, and 2 means it's in the upper region. Okay. And after non-dimensionalization, I had this total depth of the channel being 1, and I have the depth of each fluid from the upstream denoted by H1 and H2. And with the prime, I mean they are downstream parameters. Okay. So what do the equations look like? Okay, I forgot to mention this is all irrotational. Here I do not need vorticity at all. In those numerical calculation, there's no vorticity. It's different from the surface wave. Because I said, like, Spielvogel has proved that if there's no vorticity, there's no corner. Okay. But here, because of the presence of another fluid, crazy thing can happen even without vorticity. So you have Laplace's equation in both layer, okay, for the stream function. And now we normalize so that the level curve of psi, well, psi is equal to 0 on the interface, okay, and then you can calculate the values of psi on the two rigid walls. And the Bernoulli, okay, I haven't told you the dynamic boundary condition here is a pressure continuity. Okay, so it's not like a constant pressure because now you have two fluids. Okay, so the pressure continuity condition now translates to this jump condition. So the double bracket means there's a jump across the interface. So the jump of the kinetic energy and the potential energy is a constant. All right, so that's what it says. Okay. So, but what is that constant, right? So that's still like an unknown, but this can be figured out when you impose conditions at infinity. Okay. So remember, I said at infinity things are kind of irrotational, okay, uniform flow in each layer. So if you plug that in, you can calculate that constant to be this half of the jump of the density. Okay, so that's the whole system. Okay, that's the whole system. So even to construct a non-trivial solution, there is a trivial solution, meaning that everything is flat, but that's boring, right? So if you want to see something more exciting, there's a lot of work to do. Okay, but the one annoying thing is that there are so many parameters here. Okay, I mentioned to you the H1, H2, rho 1, rho 2, and then there's the speed, the non-dimensionalized speed, which is Froude number, as in Kevin's talk as well, and the primes. So there are too many of them. Okay, so somehow this is due to this idea of Benjamin, which he referred to as conjugate flow analysis, which is a necessary condition among those parameters to be able to accommodate this kind of like a Franck type solution, which is very much first principle based. You just check, this is all completely algebraic equation. You check the conditions at plus and minus infinity, and then you make sure that you have mass conservation, energy conservation, momentum balance. Right? It's just like that. So you have like 3 algebraic equations to solve, and they're all parameter dependent. If you plug everything in and you immediately see that for this kind of a connection, this heteroclinic connection to exist, the Froude number has to be fixed through the density, and so is the downstream height. Okay, so immediately you kill these 2 parameters. Okay, and then you're left with just one and only parameter to work with, which is the upstream height, H1. All right, so that's our bifurcation parameter. Okay, so this is very helpful. So before I get to the existence result, so let me just mention one more regime which will be of interest, which is the so-called Busnesque limit. That is the limit when the 2 densities are equal. So remember, if you look at this, the Bernoulli condition here, okay, has a jump in rho. All right, so at first glance, when the jump of rho is equal to 0, you have the jump of kinetic energy to be 0. All right, but is that the case? It's not quite, because if you look at this Froude number, you have Froude number being 0 as well. Okay, when the densities are the same. All right, so if you plug in these limits, you still get some left over. Okay, so you still have this linear in Y, and that will play an important role in the gravity current context. So I just want to have everyone to keep in mind of that. Okay, so existence. So I told you that after this non-dimensionalization, after the conjugate flow analysis, we managed to have only one parameter to work with. All right. So bifurcation is what we used. It's still not quite simple because this is infinite extent. So there is a loss of Fredholmness. So the usual sort of Liavsky-Schmidt or Crandall-Lombridois does not immediately work. Right, so we've tried something like center manifold reduction. Right, but basically the result that we get is that you can bifurcate everything from the trivial state, which is like everything horizontal, being horizontal, and the interface being flat, to have some more exciting wave patterns, which is to some leading order like a pinch. Okay, so that's all small amplitude result. Okay, so epsilon is the height difference from upstream and downstream. Okay. So that's a small amplitude result, which goes all the way back to Amick and Turner in the late 80s, and we sort of re-examined this using the center manifold reduction. And in this work, we were able to even allow some vorticity. But anyhow, for the relevance of this talk, we are considering irrotational waves. Okay. So that's what happens in the small amplitude regime. And if you continue this bifurcation curve, this is global bifurcation. Okay, this is a result from well, actually, the work was completed like 5 years ago, but it just occurred like 2 years ago. We were able to continue this bifurcation curve, local bifurcation curve, to the global branch, 2 branches, plus and minus branches. The plus means it's an elevation bore, elevation solution, and the minus means it's depression. So in this like a typical solution, streamline curve along this depression branch. So everything is going down, and this is when everything is increasing. And somehow what happens at the end of the bifurcation is when you have a stagnation. Stagnation from, this is only horizontal stagnation. Remember, dy psi is u, is the horizontal velocity. Okay, but there is some some other relations that the velocities needs to satisfy, which forces this vertical velocity to be 0 as well when horizontal stagnation happens. So this is indeed something like a total stagnation. So the criterion says that at the end of the bifurcation curve, at least you will see a stagnation, horizontal stagnation. It could be both, right? But we do not know. We cannot distinguish at the point. Okay. So which means that you're going to hit some extreme wave. But what do they look like, right? So that's sort of the big question, right? So that's sort of the main projective, the main focus. Okay. So that's our main result. So we have 2 branches, the elevation and the depression. So if you trace along the elevation branch, right? So that's sort of the a representative sort of a extreme wave pattern. We can prove that for sure the wave will overturn. Okay, our framework does not allow us to go past the overturn to get to the overhang, but at least we know that the surface interface profile will necessarily develop a vertical tangent. Okay, so there will be an overturning wave at the end of the bifurcation curve. And I want to also point out that I mentioned this other rigorous proof of the surface wave where gravity is like a small perturbative, but here we do not make that assumption. So this is still order 1 gravity. Okay, so that's a definitive answer to this along this elevation branch. What happens on the other branch? Right? So the depression branch, it's not quite satisfying yet. We're still working on it. We still are left with 2 alternatives, either or. So either one sees this overturning, or if not, there will be a contact point. Okay, there will be like a gravity current kind of thing, or a cavity flow. So in the case where the 2 densities are different, the heavier being laying on the bottom, you will see a tangential contact. Okay, it's not a 120 degree. Okay, it's a tangential one, which also agrees with some of the numerics, which I didn't show you. So when we'll see this kind of a 60 degree or 120 degree, depending on how you measure it, that is when you're in Busnesque. Okay, when you're in the Busnesque regime, then you could see either overturning or you will see this 60 degree angle. Okay, and here both can happen in the sense that I think one can flip the gravity because the gravity does not occur in the Bernoulli condition anymore. So the gravity doesn't quite play as much a role here. Okay, so that's sort of the result we obtain. So in the remaining time, let me try to get to some of the ideas. Okay, it's been a long, frustrating project, and we have asked a lot of experts, some of them whom are in the audience. So we're pretty happy that finally we found a way to resolve it. So I will just mainly focus on the elevation, the overturning one. Okay, so because we can say definitive thing happened. The other one we're still trying to eliminate the overturn. Okay, so this is the main theorem of the overturning. So let me just start by explaining a little bit more from the existence result. Okay, so remember, let me get back to this slide. Remember here I said that at the end of the bifurcation branch, you will see a stagnation, okay, from either, okay, or both, but you can't tell, right? But one can in fact do better. Okay, so our idea is contradiction, proof by contradiction. Okay, so if we do not have overturning, right, then we try to prove a contradiction. Okay? So what one can show is that if overturning does not happen, then at the end of the bifurcation branch, you will necessarily see double stagnation. Okay, you will see the stagnation from both layers, not just one layer. Okay, so this takes a bit of work, but let's just take that as given. Okay, and somehow the other thing I didn't emphasize is that, as you can see from this curve, from the streamline plot, the solutions that we construct along this branch are monotone, in the sense that all the streamlines are either monotonically decreasing or monotonically increasing. And we're looking at the elevation branch, so they are monotonically increasing. Okay. So this monotonicity of this streamline, okay, in particular the surface, the interface, if you plug that into this Bernoulli's condition, you will find that at the double stagnation, this is equal to 0. Right? At the double stagnation, well, there's a unique point where you see this double stagnation, which is y equals half the full number squared. Right? Because at double stagnation, this gradient psi is equal to 0. Okay, so there's a unique point where you see this double stagnation. So that allows us to somehow to just kind of like simplify the problem a little bit by considering this kind of a toy model. Okay, very simply put, you have, okay, instead of psi, I'm just going to convert everything into u. Okay, so there's a abuse of notation. So u is like a psi with a minus sign. Okay, so I have u being harmonic in the region where it's fixed sign, say plus or minus. Okay, and in the interface, u is equal to 0. And then you have this jump condition. Okay? You have this jump condition. All right. So the jump in the gradient square is proportional to the height, y. All right. And now you wonder whether or not it can happen that you have a double stagnation point. Whether or not, well, in this case, the double stagnation means that this is equal to 0, this is equal to 0, so y has to be 0, right? So you want to disprove that you can have a double stagnation, which at first glance seems to be quite like very, very likely, because I forgot to mention that there is a certain regularity we can prove. Say, the U is Lipschitz, or the interface will become Lipschitz, and it's monotone. So as I said, we've asked around many people in this elliptic regularity theory. So to us, it's very much like a Hopf's lemma would do it, right? You have like an interface being Lipschitz and monotone. If you can have an exterior ball condition, Hopf's lemma says that you cannot have double stagnation, right? Because U is equal to 0, that's the minimum or maximum point, right? So to us, it's kind of like, it's just so close, right? Being Lipschitz is so close. If it's slightly better than Lipschitz, you're done. But Lipschitz is what you can get, right? So that's why when we were asking around, people basically said, yeah, it should be true. Give me 1 week, I'll tell you what. And then after 1 week, you say, oh, this is more complicated. Give me 1 month and then stop. But anyhow, yeah, this is basically the toy model we're looking at, okay? And I've also mentioned to you there's a monotonicity built in. There's some extra information we can utilize. But I also want to somehow make some connection with this sort of a two-phase Bernoulli problem from Cafferati, where there is a well-developed theory in the community of two-phase Bernoulli problem where people consider this kind of a very general type of a Bernoulli problem. So you have a harmonic function in the domain where it doesn't change sign, and then you have some a transmission condition, right? And there is a very nice regularity theory there. Basically says you can have boundary being like C1 alpha, which for us that's nice. If it's C1 alpha, there's no double stagnation. So for a while we thought, okay, this should do it. But then after we dig a little bit more into it, there is a condition on this function G, on this G, which says that, say, among many others, G at 0 has to be uniformly positive. But now if you look at our G, which is from here, right? If you look at our G, it's a square root of Y, which is not uniformly positive, exactly at the stagnation point, right? So again, we missed only by a little bit. That's very frustrating. It's very frustrating. Okay, so what's our main ingredient? Geometric analysis, but we found along the way that this work of Wawruka and Weiss to be very, very helpful. So many of the ideas are sort of inspired by their work. So for that, let me just quickly go over the case of this one fluid, okay, the surface wave, okay, because many of the ideas are somehow similar to some extent. So the toy problem for that single phase setup is as follows. You have a harmonic function in the one fluid region and it's 0 on the boundary. And the Bernoulli's condition is just this. It's not a jump condition, right? So again, you have a square root of Y. Okay, you have a square root of Y. That's not time, okay. So what they did is that somehow, okay, the bifurcation gives you a lot of solutions, and you want to understand what happens at the end. So the first thing one would like to do is that at the end of the bifurcation curve, you're still getting some sort of a solution to some, in some sense. Okay, so you would like some sort of a compactness along the bifurcation curve all the way till the end. Right, so you would like to be able to construct the limiting solutions, and then you look at the limiting solution, you want to show that the limiting solution will give you a 120-degree surface. Okay, but how do you ensure the existence of a limiting solution? All right, you would need some kind of a bound, okay, and the bound it naturally comes from this H1, or not H1, this the pointwise bound of the gradient. Okay, in the single fluid case, the Bernoulli's law simply states that this whole quantity is equal to a constant, and you can normalize that constant to be 0. Okay, and on the surface, P is equal to 0. Okay, on the surface, P is equal to 0, and U is harmonic. So then the additional condition you can get is that, okay, U is harmonic, this is linear, so you know that P is subharmonic. Okay, P is subharmonic, and it's 0 on the surface, so you have a minimum principal. So you know that P has a sign. So if P has a sign, your gradient square is bounded. All right, so you have this boundedness of the gradient, which allows you to extract a limiting sequence. Okay, and you are able to get this limiting sequence, and with some additional work, you manage to show that this limit also solves the problem in, say, viscosity sense, for instance. All right, and then what you do is you look at that limiting solution, and then you run this homogeneous, this blow up. You run this blow up argument. Okay, so you blow it up, all right, with the hope in mind that in order to get this 120, the limit better carries some homogeneity, right? So you scale it with some undetermined alpha power. You plug it in. In particular, you plug it into your Bernoulli's law, and then you get this alpha to be 3/2, and that gives you the 120 degrees. Okay, so that's sort of a very rough idea for the surface wave case. So we would like to do something similar, so in the sense that we would like to be able to extract a limiting sequence, and then from which we run this blow up, right? And then we immediately run into this roadblock, namely that we don't have this pressure being constant anymore along the surface. We do not know, right? We do not know that, okay? So there's no way we can use this minimum principle of pressure to bound, to get a pointwise bound of the gradient, okay? That's just not available at all, okay? So we would like to have some decay of the gradient as you approach to the double stagnation, okay? So the alternative approach we take, so let me speed up a little bit. So somehow the alternative approach we take is that we're going to give up this pointwise control, but instead we are going to be looking for some average control. But before that, let me tell you the notion of solutions, okay? Because I mentioned that we're going to take a limit of the sequence, or some sort of a compactness. So this is again from this idea. I think stems from this Bernoulli two-phase Bernoulli or one-phase Bernoulli problem, and also used in Wawruka and Weiss. This is called the domain variation solution. This is coming from the fact that the whole problem has some kind of a variation of structure. Okay, so you have this kind of an energy, and you can show that the solution corresponds to a critical point to this kind of energy where this chi is the indicator. Okay. When I say critical point, okay, this variation is not in the usual sense where you have u plus epsilon v and you differentiate with respect to epsilon. That's not. Instead, we have this u composed with this identity plus a small nudge. Reason being kind of like natural, because here what we are interested in is the level curves of u, right? So when you want to run this variation, you would like to vary the level curve a little bit. Okay, so that's sort of the rough idea. Okay, so you plug everything in, and then you calculate the variation, you get this identity. Okay, so that's, I mean, pretty complicated looking, but this is what's going to be used to generate some control. So let me get to this this replacement of this pointwise control, pointwise gradient bound. So I just said instead of pointwise bound, we're looking for some average bound. So this is sort of the auxiliary quantity, which at first glance seems a little mysterious. But if you turn everything into the complex plane, then this is like the square, the real and the imaginary part of the speed square. A gradient. Okay, let me see that. Okay, so this what we call the energy bound provides an average gradient bound. Okay, in terms of these quantities. So the capital M, I didn't mention, capital M is the maximum slope, right? We assume that there's no overturn. So every streamline has a maximum slope, okay? And we call that maximum slope to be M, okay? So basically, these guys are going to be zero if you assume a limit, if you're able to get the limit. And so that means this average, the gradient is going to be controlled by like Y, more or less. R is the radial variable. Okay, so that's sort of the replacement of the pointwise gradient bound. Yeah, I just said that. And now if you plug everything in, and then it allows you to extract a solution of variation, domain variation solution at the end of the bifurcation curve. So let me just skip this. This is about the details of the proof of the existence of the limiting solution. So I can just skip that. And then here, yeah, this complicated looking monotonicity formula allows one to guess the homogeneity. So this is like a Weiss type monotonicity formula, which is widely used in this geometric analysis context. So one can somehow, one can look at this crazy quantity M, and which takes care of this bulk part of the energy and some surface part, scaled to some power. And then computation shows, this is just direct computation, that this guy is monotone. Okay, this M is monotone. The derivative has a sign. Okay. So this allows you, well, I forgot to mention this 3/2 is important. 3/2 is important. That basically tells you the degree of the homogeneity, the gradient. Okay. So this allows you to somehow well, I just said there is this with this average the gradient bound, we can extract a limit at the end as a solution, domain variation solution at the end of the bifurcation branch, and this kind of a monotonicity formula somehow suggests a blow-up argument to give you the homogeneous degree of the homogeneity to be 3/2, which somehow hopefully would remind you of the 120 thing, right? And then you you plug everything in. Okay, let me skip that. You plug everything in, and then with a little bit of help from combinatorics, you see this kind of a 12 possible scenarios. So the 120, okay, you see that these solid lines are making like a 120 pairwise, okay? So the darker means that it's heavier fluid, lighter means it's lighter fluid, and the white means it's a vacuum. Okay, so basically near this double stagnation point, okay, without considering the fluid context, okay, you can have this 12 sort of scenarios, okay, happening. Okay, so many of them, okay, all but one contains a 120-degree angle. Okay, that's what I want to point out. Okay, but for us, the additional help that we have is monotonicity. Okay, I also mentioned to you that our profile is always monotone, so that immediately eliminates the 11, and you're left with this most trivial one. Okay, it's just nothing. Right, and that allows you to somehow show that near this double stagnation, things are asymptotically flat. Okay. So if that's the case, then there is this nice result of Ottson, which is like a quantified, I think it's a quantified version of Hopf's, which tells you that the flatness at the stagnation point gives you some sort of a lower bound of the harmonic function. Okay. And this power is very much related to the opening angle of the cone. Okay, the flatness of this local stagnation point. All right, so we had, this kind of I already showed you that we have this kind of only one remaining case where things are flat, and when things are almost flat, then you plug in certain, you insert certain cone with a wide enough angle, and you plug that into your average gradient calculation. And then there is a Poincaré type inequality involved because you have stagnation, you have gradient u equals 0. You plug in the Poincaré, and then you get to something like r to the 1/2. Okay, this is just, direct calculation. So you get this average quantity to be greater than r to the 1/2. But meanwhile, if you remember, which is hard, I know, that this quantity decays like r. So that's an immediate contradiction. And that completes the proof, right? And also concludes my talk. Thank you very much.